We're going to talk about nuclear physics. The nucleus was discovered by Rutherford. When he shot the alpha particles at well, it was later to be found to be made of protons and neutrons. Suppose you draw an atom like something like this, excuse me, a nucleus. I might have protons here and then some neutrons as well. And that leads to a question that you may not have thought of, is why don't protons repel each other and the nucleus fly apart? So scientists realized that there must be force inside the nucleus holding them together. And they named it a strong nuclear force. It must be very strong to overcome the repulsion. To overcome the electrical repulsion. But it must be also very short range. About 10 to the minus 15 meters inside the nucleus. Because once the protons get outside the nucleus, then they will repel. And that limits the size of the nucleus. If you look at the periodic table, we can only have nuclei up to about 100 protons. Once they get bigger than that, they tend to fly apart, and that's because we're getting out of the distance for which strong force works. So there are four fundamental forces that make up everything in nature, and we're going to list them from strongest to weakest. And we're going to start out with strong nuclear force. The extent of it is very short. You don't have to know that number 10 to the minus 15. It works on nucleons, particles inside the nucleus, and it holds the nucleus together. The second strongest force is electromagnetic. Its extent is infinite. It works on charge resistance. The next one is called the weak nuclear force. It is also very short inside the nucleus. Works on things in the nucleus. And you don't really need to know much about it. It's involved in radioactive decay. And then last is gravity. Okay. It is infinite. And it works on mass. Note that it's very weak, and it always attracts. It may be strange to say that gravity is very, very weak, but it is. I don't really feel a force of gravity between myself and, say, a table, even though we both have mass, and force of gravity does exist, but it's very, very weak. The only time gravity becomes important is when you have a huge mass, like the mass of the Earth. They call these fundamental forces because all forces that we feel come from these four. Okay, so if you think of a normal force, if I push down on a table, it pushes back up on me. It's actually the electrical repulsion of the electron clouds of my fingers and the table. Okay, now when they started studying the nucleus, they found out something really weird. In nuclear reactions, some mass is lost. Okay, and that lost mass they call the mass defect. The defect is something that's wrong. And one of the most important rules in chemistry was that mass cannot be created or destroyed. So they thought something was going wrong. It turns out that the mass really does get lost. And the lost mass, or the mass defect, turns into energy. Okay. A lot of energy. This type of energy is energy that powers your suns, or nuclear reactors, or nuclear bombs. And how to find the amount of energy. And there's going to be two ways. All right, so we're going to split this in half. If the mass is in kilograms, Einstein's very famous equation is energy E equals mc squared. C is the speed of light. And the energy is going to be in joules. So my mass is in kilograms, I multiply it by the speed of light squared, and I get the energy out in joules. But sometimes the mass will not be in kilograms. The mass is in atomic mass units. U for that. You do it another way. Each U produces 931 MeVs of energy. So you just multiply the number of U's times 931, and that gives you the energy in MeVs. So here are a couple of examples. Okay, how much energy is created if 1 kilogram of matter was destroyed? So we'll use the equation E equals mc squared since we're in kilograms here. So it's going to be 1 kilogram times 3 times 10 to the 8 meters per second squared. And that's going to give me an energy of 9 times 10 to the 16 joules. That's a huge amount of energy from destroying 1 kilogram of matter. Here's another example. This is going to be using the MEVs when I'm in atomic mass units. So in a reaction, a neutron decays into an electron and proton, and we have the masses of those here. Okay, so if I want to find the mass of the reactant for the reaction, it's just a neutron, so 1.008665 U. The mass of the products is the mass of the proton, 1.007276 U plus 5.48 5799 times 10 minus 40. If I add those together, I get, and I'm going to round here, 1.0078. So the mass of the products is less than the mass of the reactants. mass defect, or the missing mass, is going to be the difference. So again, I'm going to round this a little bit. That's 0087 minus 1.00780. And I end up with 0.0009 atomic mass units. Now to figure out how much energy that is, when I'm in atomic mass units, I just multiply by this negative 31 number. So energy is going to be 0.0009 U times 9. Oh, sorry about that. The program crashed. We were just in the middle of turning 0.0009 atomic mass unit energy into MeVs. So we multiply that by 931 MeVs for each U. We end up with 0.838 MeVs of energy. And that's an acceptable energy unit. We don't need to convert it to joules unless the prop asks us